Welcome back to Chem 4300. In this video, we're going to begin Chapter 12 on the quantum free particle and this concept of tunneling. So let me first go back and review some ideas from classical physics. And we know that if you have a conservative force acting on a system, that we can describe that force as a potential energy surface, and we can have a conservative force where the total energy is constant. So at any point in time, the sum of the kinetic energy and potential energy add up to a total energy which remains constant in time. Now imagine you have three different particles on this potential energy surface, and at time zero they have these positions with these total potential energy, which in this case is equal to the total energy because they're not moving at time zero. So they have zero kinetic energy, so all the total energy is in potential energy, and they're at these three positions at time zero. So what we're going to do is we're going to look at each of these particles as they evolve in time, starting with the one that has the lowest energy. And you see here, you would expect then that there's going to be a force acting on this particle based on the potential energy surface that's going to be pushing it down here towards this equilibrium point. But of course, once it gets down here at this equilibrium point, it's going to have kinetic energy, which is going to push it back up, and eventually it reaches a point here where all the kinetic energy is gone, all the total energy is in potential energy, and it reaches what we call a turning point in classical mechanics. At this point, it turns around and goes back the other way. So in a sense, it sort of hits a barrier and gets reflected back, and it goes to the other direction where it reaches the point over here, where it similarly reaches a turning point where all of its total energy is in potential energy, and then it goes back and forth like this as a function of time. This is very similar to the harmonic oscillator potential that we learned about earlier in the class. Now imagine this particle here, which has a total energy of E2, and at time zero, all of that total energy is in potential energy, and as time evolves, this particle will move down here on this potential energy surface, and it gets down to the bottom here where it has maximum kinetic energy, and then as it continues back up, kinetic energy is being turned into potential energy, but when it gets to the top, it still has kinetic energy and can overcome this potential energy barrier and move down to this next region of lower potential energy where it has even higher kinetic energy down here. But as it goes up, eventually it reaches a point where all of its total energy gets converted into potential energy. Kinetic energy is zero, and it stops moving, and then it turns around. It reaches the turning point for this particular amount of energy, and then goes back, and then, as you can imagine, then it will just oscillate back and forth between these two turning points. Now, in this case, where we have a total energy E3 up here that's higher than the other two, and at time zero, all that energy is potential energy, you can see that this particle is going to move with time. It's going to overcome this potential energy barrier, and it's also going to overcome this potential energy barrier. And if there's no barriers higher than its total energy, then this particle will be effectively free and continue moving to the right. Okay? Now that's what we expect for a classical particle. In quantum mechanics, we're going to find some very peculiar behavior. We're going to find that particles will actually have the ability to tunnel through potential barriers even if they don't have enough kinetic energy to overcome them. Additionally, we'll find that even when they encounter these barriers with enough kinetic energy to overcome them, they still will bounce back to a certain extent. So there's going to be some differences, some significant differences between the classical particle moving in this potential energy surface and a quantum particle. And that's what this chapter is about, to try to understand how those differences arise. And they arise out of the wave-like properties. So let's go back to the Schrodinger equation, and let's consider our free particle. So we're going to imagine in our particles, it divided into two groups. Those that will bind the particle to a particular region, and we saw an example of that in the previous chapter when we talked about the particle in the box. And then we're going to talk about, in this chapter, mainly potentials that don't bind the particle to a particular region in space. So as I said, we saw an example of the first kind in the infinite well, but in this chapter, we're going to look at what we call the free particle, where the potential is not able to bind the particle to any region in space. So we're going to take a simple case. We're going to say that our free particle has some total energy, but it's moving at a potential of 0. Just take the simplest possible case. So here we have Schrodinger's equation, and we're going to take the potential energy, which is equal to 0, and you can see this whole thing simplifies to this expression here for our wave equation for this free particle. Now, the wave function for this that we'll use for this wave equation here will be this stationary state here, where we just have it broken up into the time-dependent and the spatial-dependent part. And for a free particle that's traveling from left to right, we're going to have a momentum of h bar k and an energy of h bar omega, and this is what the wave function will look like. Now remember, when you see this e to the I plus I kx, that's a particle moving from left to right. And the k is just momentum over h bar, which we write in terms of energy, and this part here is the part that is only the spatial part. This is our right traveling wave. Now for our left traveling wave, our momentum is the opposite in sign, and the wave has a negative sign up here. So a negative sign means it's going to the left, positive sign means it's going to the right. Now, one thing interesting about this wave function is that there's no uncertainty in its momentum. So if I calculated the expectation value of its momentum, remember, we'll take our sandwich here and we'll do the integral, and I remember that my operator for the momentum is minus I h bar, and then take the derivative. So if we follow through with this, we use our wave function for the right traveling particle, then we substitute in, and we have to take the derivative of that expression there, which gives us back this expression here, where we have to pull out the ik, and we get to this expression here, and then you can see that this then just becomes the wave function times itself, times its complex conjugate, and of course then we know that just is going to give us back h bar k, which is the momentum that we knew we had to begin with. And if we take the expectation value for the momentum squared, we follow the same arguments here, where we're taking the derivative, p squared. So I take the derivative of that part of the wave function. When you multiply that all out, you end up with h bar squared k squared times this integral, and that's just h bar squared k squared. So if we take then the uncertainty momentum, which is just the square root of the expectation value of p squared minus the square of the expectation value of p, then that comes out to be 0. Again, this maybe is no surprise. We picked a wave function with a very precise definition for its momentum. But remember, the uncertainty principle tells us that delta x delta p has to be greater than or equal to h bar over 2. And since delta p is 0, then that means that delta x is infinity. So what we have is a wave function where we know precisely what the momentum is, but we have no idea where this particle is. So just keep that in mind. Now, another particular problem you may have noticed, I know I went pretty quickly through that last slide. If you were very astute, you might have noticed that, hey, wait a minute, I don't think that wave function can be normalized. And that is indeed true, because this wave function is an oscillation that goes through all space, right? If you multiply it, it's essentially a sinusoidal oscillation from minus infinity to infinity. So what we have is we have ends that don't go to 0. And we require in quantum mechanics that our wave functions always go to 0 amplitudes at plus or minus infinity, or at some point far away. So in a sense, what we have is we have no end. That's the problem. So we could solve this problem by, instead of using this wave function with a very precise momentum that's sinusoidal through all space, we could put together some kind of, say, Gaussian wave packet to treat our free particle. And that would probably be more physical, more appropriate picture to use. But that's going to make all the math in this chapter a lot harder, and it's not going to change any of the conclusions that we're going to have in this chapter, okay? So we're going to continue to work with this sort of unnormalizable wave function for the free particle with infinitely precise momentum. But it's not going to be a problem in terms of the kind of conclusions we're going to draw in this chapter. Okay, so what we're going to look at is we're going to look at what happens when a free particle approaches something that's called a step potential. Now, if you can imagine that when you have a metal, there are electrons in the outer shell of all the atoms that become freed up in this metal lattice. And these electrons can move freely throughout the metal. And so we can think about these electrons as like free particles moving through space. Now, what we're interested in is, imagine we have some conduction electron that's moving in some metal, and it reaches the end of the metal, and it tries to fly out of the metal into free space. Now, if it leaves the metal, it's going to leave behind a positively charged piece of matter here, right? Because the electron's negatively charged, this whole thing is neutral while it's inside. But if it leaves, this will all become positively charged, and so there'll be an attraction to bring it back into the metal. So we can approximate the potential that this electron sees with this simple step function. It's only an approximation, but it's enough for us to sort of get the ideas and simplify all of our equations. So we're going to say that when the electron is moving in the metal as a free particle, it experiences no potential. And then when it gets to the end of the metal, it has a step up where it experiences some potential associated with the attraction back to the metal. Okay? Now, so this is what we're saying, and what we're going to do is we're going to write that potential out in this form here. It's just a simple step function. We're going to say it's equal to 0 if x is less than 0, and it's going to be equal to v naught when x is greater than 0. So this is the potential, and we're going to consider what happens when our free particle, our free quantum particle, this electron, approaches this barrier. And we're going to consider the case when it doesn't have a total energy that's enough to exceed the barrier, and when it has more than enough energy to go past that barrier. We're going to look at these two separate cases and work out the details of the wave function, and then we'll combine them all together in the end. So we'll start with it approaching the step potential with the case where it doesn't have enough energy to get past x equals 0. So we're going to divide our wave function into two parts. The wave function over here and the wave function outside the metal. So we have the wave function in and the wave function out. So when we're on the left of 0, we're saying that the potential is 0. And when we're on the right, we're saying the potential is v naught. So on the left, if you take the Schrodinger equation with this potential, this is what you have for the Schrodinger equation. Rearrange it into this form. And again, I have this 2me over h bar squared, which we're going to call k squared. In this case, I'm going to call it k1 squared since it's on the left here. And this number is greater than 0. It's a positive quantity, and it's a real number. On the left, when we have a potential where, remember, our energy is lower than that v naught, we get this term over here. And this quantity, 2m v naught minus e over h bar squared, I'm going to call k2 squared. That's also a positive quantity, and that's real. But when I wrote this out, I had to put a negative sign here in order to when I did this substitution. And the difference between this case and this case is both of these guys have real numbers here, but this has a positive value in front of it. This is a plus sign here, and this has a negative sign. And that's going to make a difference when we look for solutions to these differential equations. Over here, on this side, the solutions that we can propose that will work will be oscillatory solutions like we've learned before. So we're going to propose a solution like this. We'll work out what these undetermined coefficients are, a and b, but that part should be relatively straightforward. But here, because we have this negative sign, the valid solutions will be of this form here, where we have an exponential growth and an exponential decay. So they're not oscillatory here in this case. Just that simple change in sign between here and here takes us from oscillatory to exponential growth and decay. All right? So when you work this out, you should check this, but these are the two solutions that we'll use that will satisfy these differential equations. So if we go back to, let me just go back real quick. If we go back to this term over here, this is an exponential growth term and an exponential decay term. Now, if you imagine a wave function as it's moving off in this direction in space to the right, the one possible solution is that the wave function amplitude increases exponentially, and the other is that it decays to 0. Well, this one is not physical. We can't have a wave function that's going to grow exponentially to infinity as it goes to x. So we know that this is not a physical result. So we can set that c equal to 0, knowing that that's not going to be a valid solution. So that gives us this for the wave function on the right. Now, when the wave function on the left, go back here, this function and this function meet is right here at x equals 0. So when they meet, we require that, first of all, the function always must be finite, but it also needs to be single valued. So when those two wave functions come together, they can't come together at x equals 0 with different values. They have to meet together at the same value when x equals 0. Additionally, the wave function has to be continuous. So if you're coming along and you can't have something like this or like this, where you have this discontinuous change in the wave function. It has to be a smooth transition from the left side to the right side. And to get that, we're going to require that the derivative of the wave function to the left equal to the derivative of the wave function on the right. So here guarantees that our function is single valued where they meet, and this guarantees that our function is continuous where they meet. So if we take our two solutions, again, this solution here and this solution, and we plug them into this expression, what you get are two equations. From this side, you're going to get a plus b equals d, and from this equation, you're going to get ik1a minus ik1b equals minus ik2d. So we have two equations and three unknowns. So what we're going to do is we're going to take the sum and difference, and we're going to rearrange these so that we have now just one unknown, which is d, which is the amplitude that this decay has when the wave function is at x equals 0. So we rearrange this, solve for a and b, and we get these expressions here. So now I can write the wave function for both the left side and the right side in this form. So we have the a term and the b term, which we've now expressed in terms of d and the wave numbers, and then we have the d term just on its own there on the right. And now if I take the wave function times its complex conjugate, I get the probability, and I could plot that here to give you an example. This is what we would expect, that an oscillatory behavior here on the left where the potential energy is 0, and then where it reaches a region where the total energy is less than the potential energy of this barrier, the wave function dies down in an exponential decay. Now the interesting thing is that a classical particle would never be over here. Remember in our first slide we looked at, we saw that when a particle reaches the turning point where the potential energy, the kinetic energy goes to 0 and it can't exceed the potential energy, it has to stop and turn around and go back. But you can see here that the quantum particle doesn't completely stop. It actually bleeds into, because of its wave-like behavior, bleeds into the potential barrier beyond the point where classically it would be allowed to go. So this is what we call the classically excluded region in quantum mechanics. Now, if I take the wave function, I rewrite it in terms of a and b, what's important to understand is that we have two terms here on the left and only one term on the right. On the left, these two terms represent wave function going, this is a wave function going to the right, this is a wave function for a particle going to the left. So on the left, we have wave functions associated with free particles going left and right. So in other words, it's approaching and then it's bouncing back and going in the other direction. And then this is the part of the wave function that we don't have in a classical, it doesn't have any classical analog, which is the decay and the sort of tunneling into this forbidden region here. Now, if we think about this case then, what we want to figure out is what is the reflection and the transmission, the reflected wave that's coming back. So we're going to say that A is the incident wave, that's coming towards the surface of the metal, and B is the reflected wave. So if we're going to define the reflection coefficient as the ratio of the probability of it bouncing back over the probability of it hitting the barrier. Okay, so this is our reflection coefficient. So we're going to take our expressions for A and B, and we're going to substitute them in to this, and we'll get this expression here, which then you can see when you do some more algebra, it all comes out to be 1. Okay, that seems like a lot of work to see something that's kind of obvious, that as the particle approaches this barrier, it doesn't have enough energy to overcome that potential energy, so it bounces back. So the reflection coefficient is 100% in this case. Now, even though there is some amount that's bleeding through, it decays quickly to 0, and so all of the probability is going back. So nothing escapes from the metal, but it does bleed out just a little bit there. So what we want to know then is, how far away from the surface does it get then? We know it's in this classically forbidden region. We can take the wave function on the right, and we can calculate its probability. And if you just multiply it times its complex conjugate, you get an expression like this, where I've written it out like this, and I identify this sort of decay constant, delta x, as this term right here. So that means that this is the decay constant that we have for how fast it drops. So if I take something like a copper metal, which has conduction electrons that have some total energy, so we'll have that the difference between the barrier and the total energy is 4 electron volts. We can estimate, based on this equation, what that distance is. And you can see that as the total energy gets closer to that potential barrier, it will extend out further and further. So in this case here, we can see that with 4 electron volts, you get a distance of about 1 angstrom. Now that doesn't seem very far, but that is actually on the order of about an atom in length. So for an electron that's bound to nuclei, you don't think that they would go a whole atom away in terms of their distance, but in fact, actually, as it hits the surface, it can extend out a sizable difference compared to the size of an atom. Okay, so now we have to look at the case where the total energy is greater than the potential energy of the barrier. And this is the case where classically we expect that the particle would overcome this barrier and continue flying past outside the metal and escape from the metal. Now, this is the situation we're looking at. We know from classical physics that if you have a potential like this, there's no force here, there's no force here, but when you have this big change in potential, there's going to be a force associated with that. So if we took the derivative of this, you end up with a little spike like that. That's sort of an impulse force that acts on the particle as it passes through this barrier here. And that impulse force is going to reduce the kinetic energy or the momentum of that particle. It's going to slow it down, but it's not going to stop it from a classical point of view. It's just going to cause the momentum to just drop because of this impulse that hits the particle. So the particle's kinetic energy is going to be this value on the left, but on the right, it's going to lose its kinetic energy as it passes by that barrier. So now it's going to have a smaller momentum on the right than it does on the left. So in the two regions for the Schrodinger equation, we're going to have on the left inside the metal an equation that looks like this, and on the right it's going to look like this. Now remember, in this case, the total energy is greater than the potential energy. So when I've written out this expression, I now have a plus sign here and also on the right. So we knew this side had oscillatory solutions, but now we get a wave equation when we exceed the barrier potential that's oscillatory on the right side instead of a decay. So this solution, again, is oscillatory just like before, and this solution on the right will be oscillatory with a wave number that's given by this expression here. So When we approach this barrier then, we're going to have these two wave functions. And we know that as the particle travels through, it's going to overcome this barrier and continue moving on. Now, in this model, we just have this barrier constant. We don't know, we haven't put anything in our model, and a larger barrier later that will cause the particle to bounce back and come flying back in that direction. So once it gets past this point, as far as this model is concerned, it continues on. So if you look at this wave function over here, you see that this is a left-going wave function particle, and this is a right-going particle. So we can't have it coming back, so we know that this d has to be equal to 0 because the particle, after it passes this barrier, is going to just continue on to the right. So that's the only term that we should have in this wave function on the right. So we're going to get rid of that term. And then when we get to this side, you might think that if the particle passes this barrier and it continues on, that we don't need any more this term here where it's going back to the left. But in actual fact, for a quantum particle, we can't rule out the fact that it actually hits the barrier and bounces back, even though it has more energy than the potential barrier than it needs to overcome the potential barrier. So we're going to leave that possibility in over here that it can actually bounce back. So again, going back to our requirements that it needs to be continuous and single valued, then we get these two equations from those two wave functions. So I go back here, I'll take these two wave functions, I plug them in here, and I get these two equations here, which I can then solve for A and B and C in terms of a common value, which is just A, and then plug them in to my expression here, where now I have the wave function on the left side and I have the wave function on the right side. So here we see that this is a function going forward, going from left to the right, but over here we're going to have this term, which is going to be our reflected wave. So there's a possibility that's with this amplitude here being related to the probability of it being reflected and going back, even though it has a total energy that exceeds the potential of the barrier. So if I calculate a reflection coefficient, I'll take, again, b of the b squared, so b complex times complex conjugate times b over a complex conjugate times a. When I plug in those values for a and b, I'll get this expression here, and this is no longer 1. So we don't have reflection as we expected for a particle that whose energy exceeds the barrier, but it's not 0 either. So that's really surprising from a classical physics point of view. We can now look at what's called the transmission coefficient. We can figure out how much of the wave probability goes forward. But actually one of the issues is when I calculated this guy, I didn't give you the full derivation here. In the full derivation, you need to include the probability flux, the probability per unit time, change of probability per unit time. So we needed the wave speed to be multiplied times these probabilities in order to get the proper reflection coefficient. But since it's the same on the left, going forward or back, it's the same wave speed, I didn't bother to give you the derivation. It just ends up being the value that I gave there. But now that I'm going to be doing the transmission, as it moves from the left, it has one wave speed, but once it goes past the x equals 0, outside the metal, it's going to have another wave speed because it has a reduced momentum. And so we're going to have to include that in our transmission coefficient. And so what we get in calculating this coefficient is we get this value for the transmission. And this is only good for when E over V, when we have this case B here. Otherwise, the transmission is going to be 0. So when we take the fact that the transmission plus the reflectance has to add up to 1 for the total probability, then we can get that with some algebra. This is in the homework. You can get that this expression for the reflected is given by this here. So the reflected then will eventually go to 0 is your total energy gets higher and higher and higher. When this value, the total energy, exceeds the potential by a large amount, then this just becomes 1 minus the square root of 1, and that becomes 0, and we have no reflected power left. But I can actually plot this. So we have the two cases that we solved. First, we solved the case when it didn't have enough total energy, and then we solved the case when it had more than enough total energy, and this is what we get for the expressions for the reflected coefficient. So here we see the reflection is completely 100% until we reach this point where the total energy over the potential barrier energy is 1, and at that point we start to have more energy than the barrier to overcome the barrier, and so you can see that the reflection starts to drop, but it doesn't go immediately to 0. So a classical particle would drop immediately to 0 once it exceeded the barrier potential. But here you see that it actually decays and eventually goes to 0, but it's not till you're out here to maybe a factor of 2 greater that you start to get closer and closer to 0. Same with the transmission. You see you have no transmission. Of course, you're bouncing back completely until you hit the potential energy. I'm sorry, the total energy matches the potential energy, and once it starts to exceed the potential energy barrier, then you can see you start rising quickly, that you get transmission, and eventually it levels off to 1, just like the limit for a classical particle. Okay, so this describes then the very strange behavior of the quantum particle that, as it approaches a barrier, does things that in the limits that your energy gets very large, looks like what the classical particle will do. So in the very large energy limit, we get 100% transmission and 0 reflection. But in this region here where you're just getting, your total energy is getting just approaching that potential barrier and just exceeds it just slightly, then you can see that the transition is not sharp like you would expect for a classical particle, but approaches what you get for a classical particle as the energy gets larger and larger compared to that barrier energy. All right, so that's again, that's it for this section. In the next section, we're going to look at a different potential barrier, one that actually has a little bit more applications to different issues in chemistry and spectroscopy.